Okay, I hit the go live button. You're live. See? Okay. Looks like we're live. Try it again. Okay. This is working. Put this on the tube. 1 second here. I gotta adjust some stuff. Are live. All right. Put it on Discord. Okay. All set. All right, so welcome to another Hupo stream here. We're changing things up a little bit. We're trying to get a little bit more professional. We're gonna start putting the streams, scheduling them. So on YouTube, you should be able to see the different streams that are going to happen and what they are, and then hopefully you can beforehand figure out which streams you want to listen to and which streams you don't want to listen to. We're also starting to make thumbnails. Trying to pick up on the Discord, so starting to get a little bit more legit, and definitely join the Discord and give me feedback if you're interested in specific things or you think some things work better and so on. So today we are going to be reading a classic paper here. This is a classic deep learning paper on residual connections, sometimes called skip connections. And this paper is quite old at this point, December 2015. Originally came out of Microsoft Research, and kind of the main author here, Kai-Ming He, actually went on to write a bunch of other cool papers and now is kind of a staple in the computer vision community. So this paper introduced kind of one of the key ideas of modern neural network architecture design, right? This skip connection where you have basically connections that go past layers and they help with vanishing gradients. They help kind of train things quicker. And yeah, you can see back in the day here, they were still using ConvNets. So some of the stuff is going to be a little bit outdated for sure, but it should be interesting to go back and read this with the context that we have now. Cool, let's go ahead and do it. I got myself a big mug here of yerba mate, so let's get to it. Deeper neural networks are more difficult to train. We present a residual learning framework to ease the training of networks that are substantially deeper than those used previously. We explicitly reformulate the layers as learning residual functions with reference to the layer inputs instead of learning unreferenced functions. Provide comprehensive empirical evidence showing that these residual networks are easier to optimize and can gain accuracy from considerable increased depth. Yeah, residual connections really allowed kind of deeper networks to happen. Still using ImageNet as the benchmark here and VGG nets as the generic ConvNets. This result won first place on ILS VRC 2015 classification task, so it was definitely making waves when this got released. 28% relative improvement on the COCO object detection dataset. Yeah, look at this. Our submissions to the ILS VRC in COCO 2015, where we won the first places on the tasks of ImageNet detection, ImageNet localization, and COCO segmentation. So basically, residual connections were huge when they dropped, and they won all the different challenges, right? All the different classification, detection, segmentation tasks. This was really a step function improvement in the performance of neural networks by architecture design. And I think we'd have to move forward to transformers to find something that had this level of impact. Deep convnets have led to a series of breakthroughs. Deep networks naturally integrate low, mid, and high-level features and classifiers in an end-to-end multi-layer fashion, and the level of the features can be enriched by the number of stacked layers. Yeah, so in 2015, people were still kind of impressed by the fact that deep neural networks could basically learn these different hierarchies of features without kind of any explicit feature design, which is the way that it was done before, where people would design different types of features at each level, right? They would have little edge detecting features, and then maybe they would have like a kind of a human shaped. There used to be this kind of like human shaped hog. Histogram of gradients. Computer vision, not. Yeah, this stuff here. See if I can find it, but yeah, right here. So, this is kind of what old computer vision would look like, right? Where you would basically, you would get an image, you would basically turn it into gradients. So basically the gradient here refers to the kind of black to white, white to black, kind of shades of gray. And then you would get all these vectors and you would align them with this kind of this engineered kind of feature map here that someone designed that kind of looks like a human. And if the gradients just so happen to overlap with that, then you would have a high activation and you would be pretty confident that it's a human. But obviously that stuff wasn't as good as deep neural networks, because deep neural networks basically build their own features. They kind of learn their own features, and those features actually end up being way better than the ones that were hand designed by humans anyways. So at very deep models. So yeah, in the beginning of neural networks, there was always this problem where the deeper you made your model, the longer it took to train, because the gradients had to get through all these layers. Obstacle to answering was the notorious problem of vanishing and exploding gradients, right? So basically, as you tried to push gradients deeper into these neural networks, because of the way the chain rule works, right? You end up multiplying a small number by a small number by a small number by a small number, and then by the time you get to like the first layers of the neural net, the like change that you're doing to that weight is absolutely tiny. So you'd either have to train them very, very long, or you'd have to make them shallower. So residual connections allowed you to basically push the gradients deeper and solved this vanishing and exploding gradients problem. This problem has largely been addressed by normalized initialization and intermediate normalization layers. So intermediate normalization here basically means that in between you're normalizing, in between each layer you're normalizing so that you're kind of bringing everything back so that it's nice and evenly distributed between -1 and 1 or 0 and 1 or whatever you want. So that prevents kind of just very tiny numbers or very big numbers here. Exploding gradients is also a problem, but not as much as vanishing gradients, IMO. Which enables networks with tens of layers to start converging for stochastic gradient descent. I mean, this is cute. Tens of layers. You know, now ResNet 101 has hundreds of layers, right? And transformers even more than that. When deeper networks are able to start converging, a degradation problem has been exposed. With the network depth increasing, accuracy gets saturated and then degrades rapidly. Unexpectedly, such degradation is not caused by overfitting and is adding more layers to a suitably deep model. Leads to higher training error and thoroughly verified. The degradation in training accuracy indicates that not all systems are similarly easy to optimize. A shallower architecture and its deeper counterpart that adds more layers. There exists a solution by construction to the deeper model. The added layers are identity mapping, and the other layers are copied from the learned shallower model. Okay, so they're kind of using this like thought experiment here to say, what if you had a deeper model that was just the shallower model with a bunch of identity layers on it? Okay, here's they finally introduced it here, the deep residual learning. Instead of hoping each few stacked layers directly fit a desired underlying mapping, we explicitly let these layers fit a residual mapping. So this is where the word residual comes from there. Denoting the desired underlying mapping, get out our little green here, h of x. We let the stacked nonlinear layers fit another mapping of f of x, which is just h of x minus x. The original mapping is recast into f of x plus x. So here x is identity. X is just the input. Okay, so x is what's coming in. And then you have here this layer here. They're writing it in such a way that the ReLU is like a separate thing, but normally the ReLU is just kind of included there. But x can go through this neural net layer here, f of x, and then it goes through the ReLU, and then it goes through another weight layer here. And then this residual skip connection here, right, is just taking x. The identity here just means they're not doing anything to it, right? It's just as is. And then they're adding it to the output here. So rather than the output being f of x, it's now f of x and then plus this x here. And that's before the ReLU. So they're doing this concatenation or this addition, sorry, before the ReLU. If an identity mapping were optimal, it would be easier to push the residual to 0 than to fit an identity mapping by a stack of nonlinear layers. I wonder what they mean by that. The formulation of f of x by x can be realized by feed-forward neural networks with shortcut connections. Shortcut connections are those skipping one or more layers. In our case, the shortcut connections imply simply perform identity mapping. Yeah, I mean, I don't like the use of identity mapping here. Like, this makes it sound more complicated. Like, you're just not doing anything. That's what it means. It's like you're just taking this x and you're adding it here. But they keep using this identity mapping, which is kind of like needlessly verbose way of saying that it's the same thing. Identity shortcut connections add neither extra parameter nor computational complexity. Yeah, you don't need any more parameters, right? So here, in this weight layer, you're going to have a matrix of weights, and you're going to have a potentially a matrix of biases, right? So you have to store those somewhere, and you're going to have the same thing here. But this connection here, this skip connection here, or residual connection, you don't need any extra parameters to create that, right? You can just add this to your architecture, and the size of your model is exactly the same. So you do have to perform this additional computation here, this addition, but that is actually a very easy computation to perform. So here they're basically trying to talk about how you're not going to have to increase the size of your neural net in terms of the total amount of parameters if you want to use skip connections. Look at this. Using common libraries. They were still using Caffe back then in this time period. Back when they were still riding around in horses, basically, in 2015. We present comprehensive experiments on ImageNet to show that the degradation problem and evaluate our method. We show that our extremely deep residual nets are easy to optimize, but the counterpart plane nets exhibit higher training error when depth increases. And 2, our deep residual nets can easily enjoy accuracy gains from greatly increased depth. So really what they did here is they realized that they can use these skip connections to train things faster, and then once they realized they could do that, they were like, wait, well, we can just make these 10 times deeper, and why don't we try doing that? And kind of the lesson that everybody knows at this point is if you just make your models deeper and wider and you make your data sets bigger, you're just going to get better performance. So the skip connections and residual connections were really just a way to make models bigger, right? And the bigness of the model is what caused it to be better. We present successfully trained models with over 100 layers and explore models with over 1,000 layers. The ImageNet classification, we obtain excellent results by extremely deep residual nets. Our 152-layer residual net is the deepest network ever presented on ImageNet. Okay, so they basically pushed the state-of-the-art there in terms of depth. Our ensemble has a 3% top 5 error, and it won first place. And then they won a bunch of other first places here in COCO detection, COCO segmentation. This kind of makes you realize how old COCO is, right? Like, these are very old competitions and data sets. All right. I think we should actually make this red or blue, right? Because it's red as data set. Is that our coloring scheme? I don't really remember anymore. Residual representations. In image recognition, VLAD is a representation that encodes by the residual vectors with respect to a dictionary, and a Fisher vector can be formulated both as a probabilistic version of VLAD. What? What are these? (2012) paper, aggregating local image descriptors into compact code. Okay, so that's probably a paper that's kind of like old school computer vision. You're actually like hand designing this stuff. But yeah, here they're basically saying that there's kind of these old school computer vision things that are similar-ish to the idea of residual connections. For vector quantization, encoding residual vectors is shown to be more effective than encoding original vectors. In low-level vision and computer graphics for solving partial differential equations, the widely used multi-grid method reformulates the system as a subproblems at multiple scales, where each subproblem is responsible for the residual solution between a coarser and a finer scale. An alternative to multi-grid is hierarchical basis preconditioning, which relies on variables that represent residual vectors between two scales. Dude, this stuff sucks. Like, I'm so glad that like all this stuff went away. You know, now anytime you do machine learning, you just automatically use a deep neural network. But it used to be the case that you had like these huge, just basically just books, you know, filled with all these different approaches, all these different like hand-coded things that people had designed over decades and decades, and each of them was only applicable to specific types of problems, and there was like every one of them had like a whole bag of tricks that you had to know how to use. And then deep learning came along and it basically just said, nope, none of that matters. You're going to be using the same exact architecture, the same exact method for every single problem. So the simplification that neural networks created is huge. Very understated. And the same thing is happening with transformers too, right? Where transformers are kind of eating all the other types of neural network architectures, and now you basically use transformers for everything. These methods suggest that a good reformulation or preconditioning can simplify the optimization. Practices and theories that lead to shortcut connections have been studied for a long time. An early practice of training multi-layer perceptrons is to add a linear layer connected from the network input to the output. Interesting. So even back in multi-layer perceptron days, I wonder how old these references are, 34 and 49. 1996, and then 49 is 1999. So that's interesting. People were basically, they figured out skip connections before the millennium. A few intermediate layers are directly connected to auxiliary classifiers for addressing vanishing and exploding gradients. The papers propose methods for centering layer responses, gradients, and propagated layers. In 44, an inception layer is composed of a shortcut branch and a few deeper branches. Concurrent with our work, highway networks present shortcut connections with gating functions. These gates are data dependent and have parameters. Yeah. So sometimes you'll see skip connections get referred to as a highway. I think if you actually look at the Karpathy video where he describes transformers, he actually uses the word highway. And I think that comes from this paper here, Highway Networks. So this is basically the same idea where you have these shortcut connections here that basically allow you to skip specific parts of your architecture. And they call this a kind of like a data highway. So that's kind of where the term highway comes from that some people use. And it seems like these have data dependent parts. So like rather here, right, you're just using the identity, which basically means you're not doing anything. You're just taking this X and then as is, you're just applying it here. But you could have some kind of parameterized logic here, right? So, I don't know, maybe if the X is above a certain magnitude or if certain parts of X are above some threshold, and they're calling these gates, right? But the problem with that is that then now you're going to have parameters. You're going to have parameters that specify the behavior of these gates, and it's not worth it. Right, our identity shortcuts are never closed. All information is always passed through. Yeah, I mean, and there's something beautiful here, right? Where basically highway networks had this additional complexity of like kind of a gate, right? A gate here. And then having different parameters and having some more complicated logic that either closes the gate or opens the gate or like lets specific type of information flow through. And how beautiful is it that it turns out that just removing that and having a much more simplified just identity mapping where, hey, the information always goes through and you don't need to worry about what it is actually the better solution. And there's kind of like there's some beauty in that simplicity, that the best result you get is from the simplest possible solution, right? I think we're kind of lucky that that's the case. Let us consider h of x as an underlying mapping to be fit by a few stacked layers. Okay, so we get out our math definition green here. If one hypothesizes that multiple nonlinear layers can asymptotically approximate complicated functions, then it is equivalent to hypothesize that they can asymptotically approximate the residual functions. Okay, so the wording here they're using is a little bit confusing because they're being very mathematically correct, right? At the end of the day, neural networks are a type of function approximation. They're like a technique for approximating a function, right? So what they're saying here is that their neural net is trying to approximate a function h of x, right? And they're saying that the residual function, which is h of x shifted, right? So minus x, so just basically you're shifting it a little bit, should be able to get approximated by a neural net as well. So nobody really uses this type of language anymore, right? Like the fact that neural nets are function approximators, they kind of mostly just like we've evolved beyond this kind of like strict mathematical definition, but that is really at the end of the day what neural nets are, is they're just function approximators. Rather than expect stacked layers to approximate h of x, we explicitly let the layers approximate a residual function f of x. Yeah, so this is the new function that your neural net is approximating, f of x rather than h of x. The original function thus becomes f of x plus x. Although both forms should be able to asymptotically approximate the desired function, the ease of learning might be different. This reformulation is motivated by the counterintuitive phenomena about the degradation problem. As we discussed in the induction, if the added layers can be constructed as identity mappings, a deeper model should have training error no greater than its shallower counterpart. The degradation problem suggests that solvers might have difficulties in approximating identity mappings by multiple non-linear layers. With the residual learning reformulation, if identity mappings are optimal, the solvers may simply drive the weights of the multiple non-linear layers towards 0. I don't know. Here they're just kind of like trying to. This is just all like theorizing, right? It's like I don't think that's how. We don't pretend to know how neural networks actually optimize their black box, like feature space. But here the stuff was simple enough that they kind of had ideas about what's actually going on underneath. It is unlikely that identity mappings are optimal, but our reformulation may help to precondition the problem. If the optimal function is closer to an identity mapping than a zero mapping, should be easier for the solver to find perturbations with reference to an identity mapping than to learn the function as a new one. The learned residual functions in general have a small responses, suggesting that identity mappings provide reasonable preconditioning. So I think basically what's going on there is they were afraid that if you kind of skip, if you skipped too much stuff, right, you wouldn't ever have kind of information flow through these layers, right, and you would basically result in these kind of like collapses of the function approximation technique where you would just end up what they have in here called zero mappings or whatever. The weights of the multiple nonlinear layers would drive towards 0, right? So they would basically say that because you're providing this like identity path like around the layers, you're never going to get anything that goes into here, and then over time these weight layers are just going to become zeros and just become identities, and you're basically just not learning anything. But by the magic of the universe, it just so happens that that's not the case. We adopt residual learning to every few stacked layers of building blocks is shown in figure 2. Okay, figure 2 is down here somewhere. Okay, here we go. No, this is figure 3. Okay, so we don't know where figure 2 is. Formally, in this paper, we consider a building block defined as... Okay, so here's your standard... No bias here. Important to consider. So you have your weight matrix, which is your standard weights inside of a neural net. Sometimes called theta, right? The parameters of your neural net. You have x, the input. So this is just a linear layer here that's just multiplying these weights by this input. And then the plus x here is the residual connection where you're just basically adding the x at the end. So it's going around this weight matrix. And that's the output. So x and y are the input and output vectors. F of x wi represents the residual mapping to be learned. There's two layers here, f w2 sigma w1 x. Sigma denotes the ReLU, so sigma is the activation function here. Right, so here, this is w1. This is going to be sigma, the ReLU, and then w2 is the second weight layer. The biases are omitted. For simplifying notations, yeah, so no biases here, just weights. The operation f plus x is performed by a shortcut connection and element-wise addition. We adopt the second nonlinearity after the addition. Yeah, I wonder if that's going on. Like, let's actually look at the transformer. Attention. All you need. I'm wondering if the residual connection is applied before the it's hard to tell. So I was trying to see if this residual connection here, right, is happening before or after the nonlinearity or the activation function, right? So is the ReLU here or is the ReLU here? Kind of seems like it's almost after it, right? This is not only attractive in practice, but also important in our comparisons between plane and residual networks. We can fairly compare plane residual networks that simultaneously have the same number of parameters, depth, width, and computational cost. Yeah, so the nice thing about these residual connections is that you can basically very easily compare with and without them. So it made for a very good idea in terms of papers, right, where you have to kind of show some kind of experiment and show your results. The dimensions of x and f must be equal. If this is not the case, we can perform a linear projection by the shortcut connections to match the dimensions. Okay, so what they're saying here is that, right, when you are taking this x and you're adding it after you do the multiplications here, maybe this x is going to be a different dimension than what's coming out of here. So what you're going to do is sometimes you take this x and you have this matrix here, WS, right? You perform a linear projection which takes your x, which is going through the residual path or the skip connection path, and makes sure that it's the same dimension as what comes out of the standard path, if we want to call it that. We can also use a square matrix, but we show by experiments that the identity mapping is sufficient. Economical. Interesting use of words there. Form of the residual function f is flexible. Experiments in this paper involve a function f that has 2 or 3 layers, while more layers are possible. But if f only has a single layer, equation 1 is similar to a linear layer, for which we have not observed advantages. We also note, although the above notations are about fully connected layers for simplicity, they are applicable to convolutional layers. The function can represent multiple convolution layers. The element-wise addition is performed on 2 feature maps. Yeah, so there's nothing about skip connections that is limited to linear layers. You could do this with anything, right? And actually, as we saw in the transformer paper, they have skip connections between attention heads. So you can even do it with attention heads in between. So this concept of these skip connections is actually quite general and can be applied to a ton of different types of neural network architectures. Plane baselines are mainly inspired by the philosophy of VGG nets. The convolutional layers mostly have 3x3 filters and follow two simple design rules. For the same output feature map size, the layers have the same number of filters. And if the feature map size is halved, the number of filters is doubled so as to preserve the time complexity per layer. So these are just kind of generic convolutional network rules of thumb, but these have also kind of disappeared. Nowadays, actually, most of the convnets that you see are the result of a neural architecture search, which is basically a computer sat there and like tuned the size of the filters and all of these different things, the feature map size, the number of channels. Like the numbers for those now are basically just the result of this giant hyperparameter tuning called neural architecture search. So, but before that, before people did that, they would have these kind of little rules of thumb, right? Such as this one, that if you're going to make the feature map half as small, then double the number of channels. But not worth remembering that stuff because it doesn't even matter anymore. Network ends with a global average pooling layer and a 1000-way fully connected layer with a softmax. Okay, so this is just a classification head for Cocoa, probably. Our 34-layer baseline has 3.6 billion flops, which is only 18% of VGG19. Fewer filters and lower complexity. So VGG19 is, I think, at that point, it might have been the state of the art. So it might be the one that achieved the highest on Cocoa detection and Cocoa segmentation. So that's why they're comparing to it. But they're just kind of going to show how VGG19 actually has some complicated stuff, and it's actually significantly larger here. So they say that, right, their 34-layer residual convnet has basically 3.6 billion versus 19.6 billion. So like, whatever that is, 1/5 of the number of flops required. So here they have the plane and then residual. So these have the same exact number of parameters, right? That's the beauty of like the residual connections, that you can very directly compare. So you can see how the plane one, the only path for the gradient to follow is right through all these conv blocks, right? And you can just feel how slow it's going to get, right? It's like, in my head, I'm thinking of like one of those videos where they have like a guy and he shoots a bullet through like 10 different layers of glass, right? It's just, by the time you get to that 5th layer of glass, the bullet's going so slow, right? So just think about the gradient going through all these layers here. By the time it gets here, it's just going to be nothing, right? Versus here, right, with these residual connections, like the bullet will go past multiple panes of glass, so it still has the same amount of like velocity and momentum and impact here as it did here. So this kind of allows it to go deeper. The gradients can very quickly go through and penetrate this giant stack of deep neural net layers. And then here they compare it to the VGG. You can see how this is a little bit more complicated. There's like a bunch of intermediate pooling layers here. There's a pool here, there's a pool here. Example network architectures for ImageNet, the VGG19 model as a reference. And then they have their plane 34 parameter and residual 34 parameter. The dotted shortcuts increase the dimension. Yeah, so as they were saying, sometimes the residual connection, right, this residual connection from here to here, the dimensionality of what comes out of this 3x3 conv block is the same as here, right? You have 256 channels, a 3x3 conv. But from here to here, the dimensionality changes, right? Here you have 256 channels, now you have 512 channels. So you need to basically, if you want to have a residual connection from here to here, you need to increase the number of dimensions. So that's what they're showing you with this dotted line here, is they're basically saying that some of these residual connections, you have to increase or change the number of dimensions so that you can add them cleanly. Based on the above plane network, we insert shortcut connections which turn the network into its counterpart residual version. The identity shortcuts can be directly used when the input and output are of the same dimension. When the dimensions increase, we consider two options. The shortcut still performs identity mapping with extra zero entities padded for increased dimensions. It's kind of interesting. So it's literally zeros is what they're using. The projection shortcut is used to match dimensions for both options. When the shortcuts go across feature maps of two sizes, they are performed by a stride of 2. Implementation. Our implementation for ImageNet follows the practice. The image is resized with this shorter side randomly sampled 256 480 for scale augmentation. A 224 by 224 crop is randomly sampled. Okay, so they're basically randomly cropping the input image. So Cocoa has different image sizes, right? They're not standardized. Something like MNIST or ImageNet, every image in MNIST and every image in ImageNet has the same exact size, but I think Cocoa does not. So you have to basically, you have to either crop it or scale it. And here they're choosing to crop it. So in a way, this is actually acting as a form of augmentation, right? Because every time you feed, every time you perform an epoch and you train over your whole data set, right, the crop that is randomly selected for each image is going to change. So every epoch is going to have a slightly different crop of every image. So it's like a form of data augmentation. They also have horizontal flip as another augmentation. Per pixel mean, this is like you can if you take every single image in ImageNet, right? There's 3 channels, red, green, blue. And then there's some distribution of red pixels and blue pixels and green pixels, right? There's some here, histogram of pixel values or something like that. Yeah, something like that. So there you go. So for something, I don't know if this is ImageNet, but any kind of image, right, there's going to be different values for the red, green, and blue pixels. And these distributions are not going to be like perfectly on top of each other. So when you're training a neural net, you want everything to be as close to a zero, as close to a Gaussian centered around 0 with a unit variance, right? So one trick that people used, especially back in the day here, is to basically say, okay, well, what is the average, what is the mean like blue pixel value, and let's take all the values of blue pixels and subtract that mean, so at least we're centering it on 0, right? We might not be able to shape this so that it's a nice little Gaussian, but at least we can make sure that it's centered on 0. So that's what the per pixel mean subtraction does. It kind of centers the distributions for each of the color channels. Then they're doing some standard color augmentation. They're doing batch normalization right after each convolution and before the activation. SGD, gradient descent, standard. Mini batch size of 256, which is quite big, to be honest, like 256, 224 by 224 images. It's not insignificant. The learning rate starts from 0.1 and is divided by 10 when the error plateaus. So they're doing a learning rate scheduling here, right? Nowadays, people have kind of more complicated forms of learning rate scheduling, but this is kind of the most basic one here, right? That's a huge learning rate too, right there, right? 0.1, like that's crazy high learning rate. highlight that. The models are trained for 60 times 4 iterations. We use a weight decay of 0.1 and a momentum of 0.9. Do not use dropout. Huh, okay. Yeah, I remember this. There was a period where suddenly dropout was like kind of out of fashion, and like people thought that it was actually negative, and like people stopped using dropout. But dropout as an idea is still pretty good. It's like this idea that like your network should be robust to kind of removing parts of it, right? And I feel like it's come back, and I see dropout all the time nowadays. So yeah, it's interesting that just the times that this was released, people were kind of dubious about the use of dropout, but it's kind of come back in sphere. In testing for comparison studies, we adopt the standard 10 crop testing, average scores at multiple scales. We evaluate our method on ImageNet 2012 classification dataset that consists of 1,000 classes. The models are trained on 1.2 million training images. They're small. And evaluated on the 50K validation images. First evaluate 18 layer and 34 layer. 18 layer plane net. Okay, so they have a couple different depths here. Architectures from ImageNet. Building blocks are shown in brackets with a number of blocks stacked. Downsampling is performed by conv3.1, conv4.1, and conv5.1 with a stride of 2. Different conv blocks here. 7x7 kernels, for example. Or no, this is the output size of the feature maps once you do that. This is the number of channels here, or the dimensionality of the feature maps, 128, 256, and then eventually 512. 152 layer, this is the deepest one they train, I think. Yeah, 248 dimensional 1x1 feature map by the end of this. I think the big drops here are the learning rate schedules. So notice how they fall exactly at 15 epochs and 30 epochs. Or actually, these are not epochs, these are iterations. So whatever, 30 times 10 to the 4th divided by the size of the data set. That'll be the epoch for this, but they just have it here in iteration numbers. But I think that's what they're doing here. These are the learning rate schedules. So you can see that the plane network. So this is the 18 layer and the 34 layer without the residual connections. You see how they actually kind of perform the same, right? They end up having the same. They kind of converge to the same point. But here, residual connection, this is the same exact network with the same number of layers, the same number of parameters trained on the same data for the same amount of time. And you can see here the difference, right? Especially with the depth. The greater depth just gives you better performance, right? And that greater depth is enabled by these residual connections. So this is really the proof here, right here. Right, because these are so similar, right? This network and this network, they're basically identical. They're trained on the same thing for the same amount of time, same epochs. Everything's exactly the same except for the skip connections, and you can see how much of a difference they make. And one interesting thing to note here is that, look at this part here. So at the very beginning of the problem, the shallower network actually learns a lot quicker. If you don't have skip connections, right, the shallower network is going to learn a lot quicker. The deep network is actually going to take a while to get started because it's just so deep that the gradients can't penetrate. But with the residual connections, look at this. The deeper network actually learns way quicker. So it's not just about the performance after the kind of like long performance after you train for a long time, which is still impressive. It's also just the fact that you can train these things just way quicker. Like they get to a pretty good score pretty quickly if you have these residual connections. Top 1% error. Yeah, so I mean this is basically just the graphs but in table form. We argue that this optimization difficulty is unlikely to be caused by vanishing gradient. These plane networks are trained with batch norm, which ensures forward propagating signals have 0 variances. So non-zero variance basically means variance is like the width of your little Gaussian, right? So if your variance is very big, that means you have potentially very big negative numbers, very big positive numbers. But if your variance is very, very small, that means that all your numbers are basically very, very close to 0. So they're saying here that because they do batch norm at every single layer, that means that the signal is getting kind of amplified at every single layer to make sure that it doesn't have like a very, very tiny 0 variance. Yeah, I mean, this is important here, right? It's that they conjecture that deep plane nets may have exponentially low convergence rates which impact the reducing of the training error. The reason for such optimization difficulties will be studied in the future. So, like in this time period, right, in 2015, back in ancient history, it's like they still thought that people still thought that we were going to be able to understand completely what's going on here, right? And they were like, hey, we don't really know why this necessarily works better, even though we did batch norm. Because we did batch norm, we don't think that it's the vanishing gradients. So we have this theory about why it happens, but we're not 100% sure, and we'll figure it out in the future. But it's interesting how like more and more people just cared less and less, right? Every year that went by, they were like, actually, we don't really understand why these like specific choices of specific architectures and things are really making, like, what is actually driving the performance here. People just stop caring. They don't really care anymore. They don't necessarily understand why transformers work better than convnets. They just basically say, let's just try a convnet, let's just try a transformer and see which one works better, and then just use the one that works better. Baseline architectures are the same as the above plane nets, expect that a shortcut connection is added to each pair. We use identity mapping for all shortcuts and 0 padding for increasing dimensions, so they have no extra parameters. Yeah, this makes it very easy to compare. 3 major observations. Considerably lower training error for the resnets than the non-resnets. The resnets converge faster. Here they're comparing it to other networks here. So you have VGG 16, which is just a smaller version of the VGG 19. Googly Net, and then PreluNet. They're kind of ancient networks that don't exist anymore. They're just kind of showing you that they have the best performance. These were pretty good scores. So like here, for example, in 2014, the winner of the competition got 8.4, and then their model got basically half of that, 4.4, half, or top 5 error. identity versus projection shortcuts. So we have shown that parameter-free identity shortcuts help with training. So parameter-free identity shortcuts here being just literally passing the input, or basically just taking what's here and then just adding it here. So you're not doing anything. You're performing an identity mapping, which is just like a overly verbose way of saying you're not doing anything to it. And projection shortcuts are the ones where they have an additional, they have some additional parameters here. So basically they're just like taking the, whatever this is, 256 dimensional and mapping it to 512 dimensional so that they can add it here. Right, and they're seeing, okay, well, is there a difference here? And let's see. All three options are considerably better than the plain counterpart. Projection shortcuts are slightly better than zero padding shortcuts. We argue that this is because the zero padded dimensions in A have no residual learning. C is marginally better than B, and we attribute this to the extra parameter. Projection shortcuts are not essential for addressing the degradation problem. Yeah. So basically here they're showing you that the identity shortcuts, which is just the simplest possible thing, is totally fine, and you don't need to be doing any extra kind of mapping or zero padding or any kind of weird shit when you pass it around. No problem, dude. We describe our deeper image nets. Do it on 2x speed. A2. Yeah, if you probably already know this trick, but like you should definitely watch, like, podcasts are very good, but like any kind of video where most of it is like kind of audio, the 2x speed or 1.5 speed, like that's the way to do it for sure. You can chew through way more content that way. Because of concerns on the training time that we can afford, we modify the building block as a bottleneck design. For each residual function, we use a stack of 3 layers instead of 2. Parameter-free identity shortcuts are particularly important for the bottleneck architectures. One can show the time complexity and model size are doubled. Okay, so these are the big ones here. The 101. ResNet 101 is still used. Like I've used that like recently. So it's interesting how this, like, at this point almost 10-year-old network is still in use. And then they won the top place with this ResNet, which is really impressive. Yeah, and you can only imagine the hype, right? Like at this point in time, people were just like, after this paper, they were like, holy shit, we figured it out. We just need to make extremely deep neural networks with these residual connections, and then we're basically, the sky's the limit. I mean, I'm excited, right? Even though this is an old paper and like I already know where it ends up, but CFAR10 dataset. This is a crowd favorite. I think red. Yeah, red is our dataset color. And then blue is our numbers. So 50K training images, 10K testing images, and classes. So CFAR is significantly easier than Cocoa, for example, or ImageNet. .32 by 32. I thought. Oh, MNIST is 28 by 28. CFAR is 32 by 32. Here's their little tiny convnet that they're making, and then they're adding residual connections to this tiny convnet. Our residual models have exactly the same depth, width, and number of parameters as the plane counterparts. So good. They loved that. These models are trained with a minimum batch size, or mini batch size of 128 on 2 GPUs. I don't even tell you what those are. Start with a learning rate of 0.1, divide it by 10 at 32 and 48K iterations, so also a learning rate schedule here. Follow simple data augmentation, padding, random cropping, random horizontal flipping. Ooh. How's it going? Back to the stream. Bold lines denote testing error, training error. Yeah, so this is basically the same as kind of the earlier graphs where you see how without these residual connections, the shallower networks train quicker, and these deep networks are basically lost, like they just can't train too long. But once you add the residual connections, the deep networks not only train quicker, but just get to a final point that's way better than all the shallower ones. Standard deviations of layer responses. So this is like at each layer in this ResNet. So right, ResNet 101, this black line has 100 layers. So the standard deviation is going to tell you kind of like how much. This is a proxy for like kind of the vanishing gradient problem, but because they're applying batch norm, it doesn't really matter. I don't really know what they're trying to get to here. Right. After batch norm. So like they're normalizing this. So like it's going to be close to 1 because that's what the batch norm is trying to do. It's trying to make it 1. Okay, let's see. Maybe they explain a little bit better what they were trying to get at. The responses show the standard deviations of each of the layer responses. The responses are the outputs of each 3x3 conv layer, after which batch norm and before the nonlinearity, or the ReLU in this case. For ResNets, this analysis reveals the response strength of the residual functions. ResNets have generally smaller responses than the plane counterparts. These results support our basic motivation that the residual functions might be generally closer to 0 than the non-residual functions. We also notice that deeper ResNet has smaller magnitudes of responses, as evidenced by this. Okay. When there are more layers, an individual layer of ResNet tends to modify the signal less. Okay, that's kind of more interesting. When there are more layers, the individual layer of ResNets tends to modify the signal less. There's like kind of an incredible depth to that statement, you know, where in deeper networks, deeper neural nets, it's not that each neural net or each layer is doing more things. It's actually the deeper you make it, the less each layer is doing. feel like we could spend a whole week just thinking about what this means. Exploring over 1,000 layers. Okay, so they try to do something crazy here and try to train a model that has 1,000 layers. A 1,202 layer. Still open problems. The testing result of this 1,202 layer network is worse than our 110 layer. Yeah, that's kind of sad, right? You can see how, like, when the Kai-Ming He, the guy who was performing these experiments and writing this paper, he just saw this pattern and he was like, holy shit, if I go from 10 layers to 50 layers to 100 layers, it just keeps getting better and better and better. And then you could see how he probably thought, what if I do 1,000 layers? And then he did 1,000 layers and it just didn't work as well as the 100 layers. That was definitely a moment of sadness. Because imagine if he would have found the 1,000 layer network actually worked better than the 100 layer network. Then we'd be living in a version of our universe where people are training like million layer networks. Okay, and here they're basically gonna give you the results on object detection. Our method has good generalization performance on other recognition tasks. Here we are interested, blah, 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 mean average precision. We won first place in the COCO and ILS VRC. Yeah, these guys like took home every single prize in 2015. And then these are just basically tables of the performance improvements. So here, for example, you have VGG16 versus their ResNet 101. You can see here, for example, boat, you went from 65 to 80. Let's see another big jump here. Table, 65 to 80. So these are huge jumps. They added a couple different tricks here. Box refinement, context, and multi-scale testing. Getting a little bit of performance there, but it's not like huge. Pretty cool. So that is deep residual learning from image recognition. This is an old paper, December 2015, came out of Microsoft, but at the time it was really amazing, exciting work. It beat pretty much all the benchmarks and all these challenges, the COCO, the ImageNet, and it really set in place this idea that there was a lot of potential improvements, and like people realize that, hey, you can make small architecture changes that are going to drastically improve the performance of your neural nets. And you could maybe even say that transformers, right, like the transformer paper would have never happened if there wasn't ResNet paper, right? Because they probably wouldn't have thought that changing the architecture would do much. But I don't know, maybe I'm psychoanalyzing the motivation of researchers too much, but very cool paper for sure. The simplest answer is the best. Identity mapping, or just taking the X here and just adding it over there. Cool. Thanks for listening. Hope you maybe learned a thing or two. If not, like and subscribe anyways, and I will see you guys tomorrow.